Hi, I'm Kevin Knowles. Today is Sunday, June 28th, 2020, and I am here filming this about these because we are still not done with coronavirus, and these are going to help with fixing it. There's 4 of these sensors done so far, and they are all exactly the same, so why have all 3 when it's easier to talk about just the one? So that's what we'll do. Now, the way these things are set up is there's a connection on the side here, screw terminals, where you can connect a power switch. I just screwed a switch directly in so it's easier. And right now, all I have on it is this test program to show that everything's working as intended. Top line, you have pressure in centimeters of H2O. B indicates that we're running on battery. B equals, that's our battery voltage. VS equals, but essentially it indicates which source you are running off of. And if I plug in either 12 volts through this port or 5 volts through micro USB here, you'll see a couple things happen. First, green light's going to come on to indicate that main power is now present. You may not be able to see it, but there's a light on down here on the power boost. That's what this board is, indicating that it's charging. A company called Adafruit makes this thing they call a power boost, and essentially it's an uninterruptible power supply for 5-volt projects like this one. That green light and that charging light would come on regardless of whether we use this port or this port. They are essentially interchangeable, except that the 12-volt port here has some extra filtering going on. The assumption is that if you're using USB, you have already done all your filtering homework and it is already all set to go. So no extra filtering is going to happen in that case if you use the micro USB. Not that it's necessarily necessary, especially for software testing and so forth, but we definitely need it on 12 volts since there's a giant DC motor run off the same supply. Now, if I start pushing these buttons, we'll get an extra character on screen to show which one we're pressing. So there's right and left, and all the other buttons correspond to some kind of test. Down, there's our backlight test, and you can also see the down arrow, or the V. And the remaining 3 buttons are buzzer tests. So, here goes medium alarm, and high alarm, and low alarm. And those buttons correspond to confirm, up, and cancel. So, that's all the buttons. There's one other bit of functionality I'd like to add to this program, which is, I don't know, push 2 buttons simultaneously and it'll go into a discharge for storage mode. Lithium-ion batteries do not like being stored for a long period of time if they are fully charged or fully discharged. So the idea is that putting it in storage mode would you just leave it on until the battery hits 3.6 or 3.5 volts, and then you can, then the alarm goes off and it just says, hey, I'm ready to be stored. Let's see, what else is there? If we flip it over to the back here, we have the LCD driver chip, a potentiometer for contrast control. This is quite delicate. Be careful when you're turning them. The end stops especially are delicate. Decoupling for this chip, capacitive decoupling, and then the other 6 spots here are address settings for this chip's I2C capabilities. You drive the display through this chip, basically, by I2C, rather than having so many wires coming from the microcontroller. So let's turn this off and remove the microcontroller board. The microcontroller is on a separate board since originally we thought we were going to have a whole lot less time than we ended up having, and we already knew how to use this setup, so that would have been the easier way to build all of this. Now that we have more time, it's kind of regrettable that we didn't put the microcontroller on here, but to put it on at this point is it's just more work than it's worth, since everything else is already set up and working. A couple bodge wires. This one's for fixing the backlight, this one for fixing, actually it's to do with reading those battery and VS voltages. Essentially you need to turn off the ability to read those lines while the system is off, otherwise really weird stuff happens because of ESD protection diodes in the microcontroller on the ADC pins. So this right here, this is the pressure sensor. It has oh boy, awful lighting. It has 2 ports, and those ports, this one here is the it's positive pressure, this one's negative. So if I apply pressure here, it'll read positive, apply pressure here, it'll read negative. This 4-pin screw terminal is I2C, 5-volt power, and ground. And they're brought out just so that if we decided to not use this sensor, or we decide we need some other functionality on this board, well, we have I2C available for making that happen. And then this 2-pin screw terminal is for the power switch. Short them together to turn the system off, or open them, disconnect them to turn it on. And I have a screw stuck in there just to make it easier to mess with. These standoffs in the corners, that's part of how this will mount to the inside of the control box. The battery here, just a standard lithium-ion 18650 size battery. The one special thing about these batteries is the manufacturer has a locked bill of materials and production scheme for them, production process, I guess. And the idea is that it's a much more controlled setup, which is exactly what we need for a device that's potentially going to be helping save people's lives. On the microcontroller board here, this is the standard Arduino header layout. So if you have an Arduino board that doesn't interfere with these 3 components, you could just plop a standard Arduino on it and program it in Arduino. I do not recommend doing that, since the Arduino interface sort of hides away lots of things about how your project actually works, as opposed to programming in C, where you can, well, see everything, but you can do it. And that was the main feature, just in case somebody else sees this and goes, hey, we want to be able to use this too. How can we do it? Well, there you go. We've made it just that much easier. Back to this board here. Standard Arduino layout, and then this header up here is quite important. When the board arrives from Microchip, it's just this. No headers, no anything of the sort. So, headers need to be populated. It's the second row in. They've outlined exactly where the headers need to go, and again, the second row in and outlined. And this corner, this is the critical corner. This resistor here, it's actually a jumper, 0 ohms, R300. If you remove that and install a header along here, it is possible to set the voltage that, set where this board draws power from. So either the micro USB port or this pin right here labeled VIN. And the VIN setting is what we need so that the shield can power this board. So, install the jumper, install the header, put a jumper on the header so that it's to the your left side. That will allow this board to run off of the shield power. Take the jumper off, place it on your right side, and it will run off of USB. We don't want that, because then you need separate power for this board. Camera ran out of space, so here we go, recording again. And where was I? Yes, we need this jumper on the V-in side. So we'll put it back there, and I actually won't put that on just yet. Let's go over to the schematic for this setup, and I'll talk through the design in a little more detail. So, 12 volt input here, that's this over here. 1800 milliamp fuse, that will be, the power supply is going to change a little bit. And the reason for that is the one here, I originally designed it with a 400 milliamp fuse. Yeah, the whole system will draw less than 400 milliamps, but only when the battery isn't charging, and we do kind of need to be able to charge the battery. So that was a mistake that this newer revision will correct. So, the other 3 units do not have that fuse installed. In other words, you cannot use the 12 volt input. There's just no, there's no fuse, so there's no path. So, next in line is a transient voltage suppression diode, TVS diode. That's to help with ESD and so forth on the 12 volt input. Capacitor here to suppress any ripple from the large DC motor that's on the same 12 volt supply, and then a conducted EMI filter for anything higher frequency. The design and the values for that filter came from the data sheet for this component here, which is the DC to DC converter here, which is an IMM0512S05. That takes 12 volts in, steps it down to 5 volts out, and I want to say max input draw of something like 650 milliamps, max output 5 volts 1 amp. And what's next? Well, the green power light here that you saw come on. Can I switch these and yeah, a little better. This LED here is to indicate when main power is present, be it from the 12 volt input or what I'll get to in a moment, the 5 volt input on the power boost. So that light comes on just to say that main power is present. Next in line is the power boost. The Power Boost 1000C is made by Adafruit Industries and an uninterruptible power supply for 5 volt projects. So 5 volts in and it will charge a battery and power your project simultaneously, or remove main power and it automatically switches over to running your project off of the battery. There's a few connections on it that we need to worry about. First is enable here. This enable line just turns the thing on and off. You ground it, the system turns off. Connect it to VS and it will turn on. It takes the battery voltage and steps it up to 5 volts, or it just passes the other input straight through. It actually seems to do a bit of a step up as well, since VS, which is from the first chip in the set, that tends to read 4.6 volts if you're giving it 5 volts, or it reads a couple tens of millivolts below the battery voltage if only the battery is present. So VS can indicate which source you are using, and it's involved with turning the power boost on. Then there's a fuse that blows at 800 milliamps, max sustained current 400 milliamps, decoupling capacitor for just general decoupling of everything, and then this label V-in is the output of the power boost, and that goes to everywhere else on the board, everything that needs 5 volts. I'll start with the buttons here. They use port D on the microcontroller, on the ATmega 328PB microcontroller, and we've provided debouncing in hardware via these capacitors, and then there's the switches themselves. So all the switches, 1, 2, 3 capacitors, 4, 5, 6, that's the rest of them. You will need to enable the internal pull-up resistors on the microcontroller board in order for the buttons to work correctly. Otherwise, you don't really know what's going to happen with them. They're floating. Let's see, what's next? So this is the pressure sensor right here. Not really a whole lot to say. I2C clock and data. Clock and data for I2C. V in, ground, that's it. What's next? We'll talk about the buzzer next. So the buzzer draws 400 milliamps peak absolute max. Typical currents, I wonder if I remember right, they were 200-ish milliamps and below. So no way are you going to sink that much current with a microcontroller. So P-channel drive transistors, pull down resistors so that the buzzer definitely stays off while the microcontroller powers up. And that's the buzzer. Also in the corner here we have the battery itself, the lithium-ion battery. This part was annoying to figure out. It is 2 P-channel transistors, 2 N-channel transistors. One of each of those is involved with monitoring Vs and the battery voltage. So this line here connects to the power switch. So basically this gets pulled to Vs or it gets pulled low. And the N-channel transistors here turn on. Sorry for the weird symbols. I'm still learning to use KiCad, the software that I used for making the schematic. So the gates of these N-channel transistors get pulled high when the system turns on. So these 2 lines here, the drains get pulled to ground, and these P-channel transistors then turn on, which means that the battery voltage and Vs get passed through to the ADC. If this sense enable here, as I called it, in other words, the power switch goes low, so you short those 2 together, this line goes low, these N channels stop conducting, these lines go high, so the P channels stop conducting, therefore battery and Vs no longer connect to the ADC. Now, why was that necessary? At first, I didn't have any of that stuff on this design, and well, you couldn't actually turn the system off. It would just appear to stay on. Oh, I should add that all of that stuff that I just described, it's on the back in this area. So here's 1 N and 1 P transistor in one package, and here's the other pair. And then the resistors that go on the gates of the P transistors. That mod wire makes it so that the gates of the N-channel transistors connect to Vs instead of the 5-volt output of the power boost. So why was any of that even necessary? Well, this is inside each analog to digital converter pin. The dotted line shows where what's inside the microcontroller. This here is, for example, the battery. And the easy way to make all this work is just put a switch. Well, what if we don't have that switch? What if it just connects straight through like that? Well, then you have 4.2 volts here, the ADC. During normal use, we'll have 5 volts up top into the unit and ground down below. So 5 volts here, 4.2 volts here, reverse biased, nothing conducts. Awesome. What happens when this goes to 0 volts and the whole system turns off? If the whole system turns off, this diode ends up forward biased, and we end up powering the rest of the microcontroller through an ADC input, through the ESD protection diode on that input. Now, ESD protection diodes are not intended to be used for high current like that, continuous current, they're for ESD protection. So long term you will damage those diodes, and we don't want to do that. So the easy to think about solution, put in a switch. The more elegant solution, put in transistors to do the switching automatically. Okay, so the resistors and transistors that drive the buzzer, those are down in here. And I think that's all the things that I neglected to point out before. So, onto the LCD. This is the chip that drives it. That is a PCF8574A I2C port expander. It's 8 input-output lines that you can use for whatever you like. And in this case, we're using to run an LCD. So, the intent was to use the design of a screen that we had used in a certain microcontroller class. That, as it turns out, was not this design. This design, unfortunately, happened to be not what I thought it was, and the website that gave the design had only the one, so I'm still not entirely sure how we came to have the wrong design in the first place, how the hardware we have from that site doesn't match the schematic they gave, but the point is, you got to be very careful when checking that stuff, and I was not careful enough, so we have a different setup. Turns out that was able to be fixed in software, and now it all works great. So why the wire? So this chip, if you look at the schematic for it, not the schematic, but a block diagram of the outputs, it appears to have totem pole outputs, push-pull outputs, you might have heard them as well. And they don't actually behave as such, they behave more as open drains. The original setup was a pull-down resistor on the gate of this transistor instead of a pull-up. Well, there was nothing to fight that pull-down resistor, so it would stay on just long enough for you to be able to tell that something had happened. So that got changed to a pull-up with that bodge wire and a little bit of Kapton tape to lift the one end of the resistor off of ground, and now that's all fixed. Other thing to point out is this potentiometer, which is this one here, that controls contrast. Decoupling capacitor, decoupling, and then these 3 resistors, these 3 jumpers, 3 resistors, 3 jumpers, those are for setting the address that this uses. That's the whole schematic. Let's see, what else is there to say about this system? This here is the somewhat cannibalized version 1. The LCD was expected to sort of mount just up here like this on a separate housing, which actually, this housing here. So that came about because we didn't think, I didn't know we were going to have room in the main control box, so have this designed, and that would mount somewhere on the main unit. But no, we ended up not needing that. Thus this, which actually also had a bunch of mistakes on it as well, like clock and data were switched for the pressure sensor, which mounts in that area. The buzzer, I had the footprint backwards because the datasheet gave the pinout from the bottom up instead of the top down, and well, now I know a bunch of things to watch for when you're designing these sorts of things. There you go, buzzer on the wrong side. Also got this pin spacing a little off, but that wasn't so bad. So that was version 1. Here's a unpopulated board. This is going to end up going to the circuits professor, Ali Gokermak, just as another example for him to show to future students. This board came from a company called Osh Park, or OSH Park. Their thing is making purple boards, so everything they make is this same purple color. And they are incredibly expensive when you start getting up to this size. So I think those ended up being something like $60-ish each, and you got 3 of them for that much at $60 a piece. This here is the new revision PCB, and it came from a Chinese company called PCB. Electrically and mechanically, it is
just as good as Oshpark's board. However, there's a lot of cosmetic sort of issues to it, a lot of little scratches, and the point is that if this was your front panel, that just would not, I wouldn't consider that passable necessarily, but we're not using it as a front panel. So the fact that this is $10.80 per board instead of, gosh, 60, this is absolutely perfect for us. Is there anything else? Is there anything else at all that I can show for these? I think that's everything. So, hope you found that helpful, and, well, that's all.